Well, we'll actually go into a lot of detail in our presentation on the topic, but the bottom line is that we wanted to update our understanding of how severe accidents progress and what their consequences would be off-site. And NRC had some pretty outdated studies that we had, and we wanted to utilize our updated computer codes, updated information about the plants and the sites, and perform more realistic modeling so that we could have better information. Based on east and southwest. So,
a turbine that runs a pump and puts water back into the reactor to keep it cool. So the steam comes out, it drives this turbine, it pumps in water, and you have a cooling cycle. And I don't think I can sort of... I do have a picture of it sort of here. So it'd be something like this. Steam comes out and then water comes in. And this is where the nuclear fuel is. But you remove the heat from this thing called it's a heat exchanger. It's called a steam generator. So,
good evening, everybody, and welcome to the public meeting tonight. And our subject for tonight is going to be a NRC project known as SOARCA and how that applies to the Sequoyah facility. And SOARCA stands for State-of-the-Art Reactor Consequences Analysis. And we're going to try to keep the acronyms down to a minimum, or at least explain them, but two that you will hear are NRC and SOARCA. And I'm pleased to serve as your facilitator for tonight's meeting, and in that role I'll try to help all of you to have a productive meeting tonight. The NRC staff, they wanted to be with you in the Sequoyah community tonight to do two things. One, to explain the SOARCA project and particularly the implications for Sequoyah. And second, to listen to your comments on this particular analysis. And as you'll hear from the staff presentations, it's pretty complex, and the staff is going to do their best job to tell you about this in an understandable manner. The NRC has also requested written comments on this particular project, and the staff will tell you about the Federal Register notice that asks for comments and how to submit your comments. But anything that you say tonight will also be considered by the staff, and there will be a written summary of this meeting along with the comments, questions that were asked, and that will be publicly available on the web. And the format's pretty simple. We have 4 speakers, and there will be brief to talk about various aspects of SOARCA, and then when they're done, we're just going to go on to all of you for questions, comments, and I just had a few real simple ground rules to help us to have a productive meeting tonight. And one is, please let the staff finish their presentations before we we wade into the comments. That way you'll hear the whole topic and you'll know what's going to be going on. Second ground rule, if you have anything to say, just raise your hand and I'll recognize you and just tell us your name, introduce yourself, and then go on with what you want to say. We don't have audio support microphones tonight, so you may have to speak up. I may ask you to speak up if I don't think that people are hearing you. And I think we can be pretty informal tonight. It's not a formal comment meeting, but your comments will be considered. So I'm not going to ask you to follow any specific guideline in terms of time for speaking, that we sometimes have to do that. But I would just ask all of you, and this goes for the NRC staff too, to try to be brief and concise and crisp. And we do want to hear from everybody. I don't think we're going to be challenged for time, but I'll go around one time for people, give them a chance to talk, go to other people, and then we'll come back to others who want to go with the second round of comment. Now, I know there's many issues, perhaps issues that project manager for Sequoyah, and he's down with us, and we also have a couple of from San Diego people, name fixers there. We have a lot of people to introduce, I guess. And you're a resident inspector. Okay. And then we have Joey Ledford here, and Edwin Lee. So I'll stop introducing people now and let Jonathan go on with the first presentation.
Thanks, Jeff. Russell, you have to let me know if you can hear me back there.
You're fine.
I'll see if I can keep up this volume. Good evening, my name is Jonathan Barr. I'm an engineer in NRC's Office of Nuclear Regulatory Research, or as we just say, research. Thank you all for coming out tonight. We're here to discuss the state-of-the-art reactor consequence analysis project, SOARCA for short, that we recently completed. The purpose of this meeting is to discuss the project's approach, results, and conclusions, and to give you all an opportunity to provide your thoughts and feedback to us. Before discussing the project, I just want to give a brief background on our Office of Research and NRC as a whole. NRC is headed by commissioners who are then supported by deputy executive director, executive director for operations, and a bunch of deputies. And then we have between 3,000 and 4,000 staff members, many of which are headquartered in the DC area, and then we have others in the 4 regional offices around the U.S. Research is one of the major program offices within NRC. We are mandated by Congress and have about 250 engineers, scientists, analysts covering a wide range of topics. We're located in the headquarters complex in Rockville, Maryland. Research supports NRC regulatory offices by providing and conducting in-depth confirmatory research on a variety of nuclear safety topics. We provide technical tools, analytical models, and experimental data needed to inform and support the agency's regulatory decisions. Our research aims to confirm whether the industry's methods and data will maintain appropriate safety margins. For example, if the Office of New Reactors is considering a new reactor design, they may ask us to conduct experiments to independently confirm the licensing information or conduct calculations to confirm that the design complies with our regulations. We commonly use contractor support from the Department of Energy's national laboratories and independent companies. And as Chip mentioned, we have been using, we've had great support from San Diego National Laboratories for the SOARCA project. And we also had support from an independent contractor, Dakota. Research also anticipates NRC's future needs and develops tools or research projects that look at technologies that could become used in the future. And this approach helps us to ensure that any potential safety issues are addressed in a timely fashion. Next, I'll discuss SOARCA. So SOARCA is a research project that we conducted to develop an updated body of knowledge regarding the realistic outcomes of potential severe reactor accident scenarios. In this study, we analyzed accident scenarios for 3 representative plants in the U.S., Peach Bottom, Soddy in the middle, and Sequoyah to the right. Peach Bottom is a boiling water reactor with a Mark I containment in Pennsylvania. Soddy is a pressurized water reactor with a large dry containment in Virginia. And of course, Sequoyah is right here with a pressurized water reactor and an ice containment. The research study had several goals. One of them was to update the quantification of the potential off-site consequences of severe accidents relative to some of the earlier studies that had become outdated, one of which is the 1982 siting study. One of the ways we did that was the use of detailed state-of-the-art modeling of the MELCOR and MAX computer codes. MELCOR is a code that models accident progression, and MAX models the off-site consequences to the public. We used plant-specific and site-specific data for each of the plants in SOARCA to make the models more realistic. Another objective of SOARCA was to incorporate plant changes that were not reflected in some of these earlier assessments. For the Peach Bottom and Soddy analyses, we evaluated the benefit of mitigation put in place after the terrorist attacks of 9/11. For Sequoyah, our focus was more on the containment response, and so we evaluated the benefit of hydrogen measures in averting early containment failure. An additional objective of SOARCA was to help enable us to better communicate severe accident safety with a variety of stakeholders, including the public. SOARCA is different from earlier severe accident studies in a number of ways. First, we focused on a limited number of important scenarios analyzed in great detail. These analyses are more realistic and integrated than past analyses through the use of updated models. For example, MELCOR and MAX, which consider and incorporate recent physical experiments. For one example, MELCOR was validated against 4 melt experiments performed in the Fetus Reactor in France. For the accident scenarios that were initiated by an earthquake, such as those that we modeled for Sequoyah, we treated the seismic impact on the road infrastructure, and that's one of the things we'll talk more about later, in terms of how it affected evacuation. And then we also used a range of assumptions for how, with respect to how low doses of radiation cause cancer. This next slide shows a flowchart of the SOARCA process that we follow, which has sort of 4 primary elements. The first was selection of the accident scenarios to analyze. After that, we determined through tabletop exercises and walkthroughs of the plants and reading all of the available documentation, we determined what actions the operators would take to mitigate those scenarios. Then we used MELCOR code to calculate the accident progression. And then for scenarios which would result in a release of radiation off-site, we then model those in MAX to examine the off-site consequences. MAX models the dispersion of radioactive material in the environment, the emergency planning and the evacuation process, as well as other protective actions such as long-term relocation. And then we calculate health consequences. After the analyses are completed, we have them reviewed by independent experts in risk assessment, accident progression, emergency preparedness, and consequence modeling. We've had review of some of the work by an external peer review committee, and we also have these reviewed by NRC's advisory committee on reactor safeguards. This Sequoyah work will be presented to our ACRS next month. On slide 8, we have a table which shows the different action scenarios for the different plants. For all 3 plants, we modeled blackout, a long-term station blackout, and a short-term station blackout. In the short-term station blackout, the earthquake that we model causes all on-site and off-site AC power to be lost, plus DC power also is unavailable, and thus is perceived core damage in the short term. In the long-term station blackout, the on-site and off-site AC power is lost. However, DC power is available, which can be used to help extend core cooling through turbine-driven systems. And thus that one can proceed to core damage in the long term. We model several variations of each of these for the different plants, some of them with mitigation, some without, and other types of variations. We also completed an integrated uncertainty analysis for one of these scenarios, which is the 3 pilot plants, which Tina will talk about later. And for the Surrey plan, we modeled 2 other accident scenarios, which could lead to a bypass accident, one of which is the steam generator rupture, and the other is an interfacing systems loss with an accident. And next, Casey Wagner will discuss some of the accident prevention modeling.
It has a steel lined shell, that's the primary containment. It has ice chests that suppress and condense the steam if there should be an accident. And it includes these igniters if hydrogen in a severe accident gets generated and gets out to the containment that will burn it at low concentrations safely. Some of the mitigation that I'll talk about later would be getting water to the steam generator. And so there's turbine-driven systems that bring water into the containment, and then they're driven by steam that's generated by removing the decay heat from the core. Surrounding the containment is this big, strong shield building that's made out of concrete. And those are the things I wanted to show in the picture there. Oh, one other thing. Key focus of the most current SOARCA project for Sequoyah was to look at the containment response, because it is a unique containment. We had already looked at a boiling water reactor. We looked at what they call a large dry containment for a PWR. And this is also a pressurized water reactor, PWR, but it has this unique ice condenser containment. So the central element for the SOARCA analysis is the application of the MELCOR and MAX codes. What is MELCOR? It's computer code for the detailed and integrated computer model. Includes modeling the reactor, all the plant supporting systems, the surrounding buildings. It's a building block code, so you can build up the novelization that surrounds it. And we work closely with the plant to get very accurate information to model the reactor, its performance, and its surrounding systems. We use MELCOR to calculate the accident scenario progression in the release of radioactive material. And so it can model mitigated accidents, but it also can model accidents that move on to the release of radioactive material. And that includes thermal hydraulic models and also some special chemistry and physics models for all aspects of the accident progression, from normal steady state conditions through the initiating loss of power, putting the boil off the water in the reactor, the heating of the fuel. Once the water boils away, the fuel will heat up, it can melt, track the movement of the fuel as it melts, and then also look at potential failure of the reactor and also of the containment. And that, if it the accident progresses to the failure of the containment, then we have a source term of fission products and gases, aerosols and gases that would be released in the environment. That's passed off to the next code, which is called MAX. And MAX calculates the site-specific atmospheric transport, so the dispersion of the radioactive material and its deposition as it moves out away from the plant. It also models the protective actions of the people in the surrounding areas. And it includes the modeling of the exposure pathways, whether it's from shine or from breathing, and it also includes the health effects. We got more coming on that. It's not my specialty. MAX models the exposure pathways and dosimetry and the resulting health effects to the public. And I wanted to point out that we use site-specific population data, evacuation data, the road networks, and weather data. And I think you've seen it on some of the posters back there, the detail that was modeled for that phase of the accident. What is mitigation? So these are very severe accidents. We've extended beyond the emergency operating procedures, and we're following 9/11, the plants have implemented additional, above and beyond all the safety systems, additional safety systems that could be brought to bear in these very low frequency severe accidents. And some of the examples include backup power to operate hydrogen igniters. That's pertinent for this plant. A special diesel generator that can withstand floods and is in a safe position that can start those up if all power is lost. There's procedures to drive these, to manually operate these steam-driven pumps that would do the cooling of the steam generators. At other plants, there's portable diesel-driven pumps for injecting water. And here's an example one over here. There are also portable generators that can power critical instrumentation. These are also post-9/11 things. And then additional air bottles to operate valves. And so these are examples of things that have happened since 9/11 to try to make our plant safer. I'm going to turn it over to Joe Jones, and he's going to tell you a little bit more about MAX. Thanks, Casey.
As Casey said, my name is Joe Jones. I'm with San Diego National Laboratories, and I've worked on the emergency response aspects of SOARCA since the very beginning, since the survey that you thought continued on with the Sequoyah. So how did we model emergency response? We used MAX code to calculate the public health consequences. The modeling was based on the emergency response elements of the modeling was based on the site-specific emergency plans, the off-site emergency plans. We used the on-site emergency plans to help understand when certain declarations would be made. We used those for the timelines of declaring the emergency. The MAX model allows us to include detailed timing of emergency response actions, such as when the public would evacuate. And we can separate the public into different groups, which I'll talk about those on the next, in a second. The timing values were based on, also based on the procedures as well as the Federal Emergency Management Agency exercise timelines that show us during exercise when sirens were initiated based on on-site declarations to off-site response agencies. Let's stick with this one for a minute. Some of the precautionary protective actions that were modeled included evacuation and sheltering. And to develop the response elements in the MAX model for that, we used the evacuation time estimate. Now, Federal regulation requires that an estimate of the time to evacuate the emergency planning zone be provided by the licensee. And NRC has guidance that provides how these ETE studies will be developed. And that guidance has provisions for demographics. So the general public is identified, special facilities like schools, nursing homes are identified, transient employees of the EPZ, and transit-dependent residents of the EPZ. So we use that information to set up different cohorts, public cohorts in the MAX model to look at specifically how different population groups would respond in an emergency. And we use the response, use the data from the ETE, we modified it as needed to address the seismic elements that we considered in Sequoyah. And we understand how that works through real-world examples from research on evacuations that the NRC has sponsored that show the public will largely follow the evacuation orders, and the emergency workers will implement their plans in the emergency. Every emergency planning zone, every site has an emergency planning zone, and Sequoyah is divided into 28 sectors. Each of these is a sector that is established based on geographical or political boundaries. In Sequoyah, we have 28 of these sectors. Now, we use the term sectors for Sequoyah, but if you look at the Surrey or the each bottom reports, you see the term emergency response planning areas. That's an ERPA, and that's another common term that's used. There's no criteria on what that needs to say, but that's a difference you might see if you look at all three studies. The residents within the EPZ receive an annual calendar that describes the Sequoyah plan and the emergency plans that are developed to protect the public. The calendar describes the prompt notification system, which are these sirens that you see, and at Sequoyah, these sirens, they're loud, but they rotate, and they cover the entire EPZ where the public are located. The sirens are operated by team members, and it's the emergency management agency. There are also tone alert radios located in different areas of the EPZ for special facilities or for other areas where siren coverage may not be sufficient, I suppose. On this particular graphic, you can see the evacuation routes, and these are in the calendar. If you want a close-up of them, you can see them on the posters. We actually modeled evacuation routes in the MAX analyses. It allows us to direct the public along the route, again, as augmented by our seismic analysis, so that we can put them on the paths that they would most likely take given the wind direction and the specific, basically the wind direction and the specific protective action that is over. And with that, I'm going to turn it over to Tina Roach.
Talk about the results now of SOARCA. Can you guys hear me okay? Before I get into the results, we first just wanted to mention what are the metrics that we're looking at. How do we report the health consequences from these potential severe accidents that we look at? So there are two metrics that we report. The first we call early fatality risk, and that is an individual risk of getting a large radiation exposure and dying shortly afterwards. And the second metric we looked at is called the long-term cancer fatality risk. And that's an individual's risk of dying from cancer years after they were exposed to radiation. So in terms of the overall results from the SOARCA project, we found potential accidents still progress more slowly and release smaller amounts of radiation, radioactive material, than were calculated in earlier studies. And on the next slide, we'll just show an illustration of that. So this is showing the iodine release. Iodine is always one of the things we care about because it's important for the calculated health consequences. And here we're comparing basically how the iodine is released over time. So the time zero on the x-axis at the bottom is the start of the accident, and going out is showing you the time in hours. And on the y-axis, what we're plotting is the fraction of the initial core inventory of iodine that's released over the course of this potential accident. Now, the reference point we're using is the 1982 sighting study, source term 1. And that's the red curve. And the blue curves are the first two pilot curves from the SOARCA study for each body in Soddy. And the green curve is the one that we just completed for Sequoyah, the third pilot curve. And what you can, I should mention, all of the SOARCA cases are what we call the unmitigated ones. So we're not crediting those post 9/11 measures. And so those tend to be earlier and result in higher magnitudes. And you see that even when we don't credit those mitigation measures, compared to that 1982 source term, the calculated releases are much later, and the total magnitude is much lower than the 1982 sighting study, which was the previous reference point. And what the later and lower releases translates to in terms of public health consequences is that the health consequences are very smaller than were previously calculated. So you know, we're meeting with them on May 19th, so that's public, so everybody can. So that
Thank you, Tina. And